So yesterday we were doing Laplace transforms. Today is the last turn for discussing the Laplace transform. Then we'll do the previous questions based on the Laplace transform, which have come in the net examination and gate examination and other such entrances. Uh, a few things that I need to pay attention on. Uh, those things I'm going to discuss at the very later stage. But right now, just want to say that let us start with doing some of the questions on inverse Laplace transform. So I have done questions on Laplace transforms, enough questions on Laplace transform. Today we are going to do questions on finding inverse Laplace transforms. Okay, so that is an important topic as it's for your examination also. Question on inverse Laplace transforms. Okay, and how to go about it. So what I'll do. Okay, so let us do a few questions on it. We want to obtain an inverse Laplace transform of 2s minus of 5 divided by 4s square plus 25. We want to obtain the inverse Laplace transform for this. Okay, so I told you on the very first day that obtain inverse Laplace transform, one of the good strategy can be to write in terms of Laplace transforms that you know. For example, you know that Laplace transform of sine 80 is a upon s square plus s a square, or you know that Laplace transform of cos 80 is s upon s square plus a square, or probably for e exponential like e power 80, you know that the Laplace transform is 1 upon s minus of a. So all these things you know. So probably one good strategy here is to try to write it in some sort of nice format. So what I'll do, I'll try to take 25 is here, so I'll try to take 4 common from here, and try to take 2 common from here. So I'll get s upon 2 s square plus 25 by 4, and then I will get minus 5 upon 2, and then you have this. I think you will take 4 common out from here now. So if you take a 4 common out from here, you get 4 s square plus 25 by 4. Okay. Now, if I have to find the Laplace inverse of this particular function, that is 2s minus 5 divided by 4s square plus 25. So we are doing today inverse Laplace transform. Okay, and we want to find. We are trying to do some questions on inverse Laplace transform, and we are trying to find the inverse Laplace transform of this particular function. Of course, this is an easy thing to do. This will be 1 upon 2 Laplace inverse of s upon s square upon 5 upon 2 the whole square minus 5 upon 4 Laplace inverse of 1 upon s square plus 5 upon 2 the whole square, which is equivalent to writing 1 upon 2, which is equivalent to writing 1 upon 2, and this is cos of 5 by 2t, and this is minus 5 by 4 sine of 5 by 2. Okay, so there is a problem. I think this is a na. So this is a, so I'll write a also here. So this is like 5 upon 2. If I'll multiply, I have to multiply 2 upon 5. So I think again I'll get 1 upon 2 only, and that is sine 5t. Is that fine? I think it is easy to see. Okay. Now let us do another question. Try to find the Laplace transform of Laplace inverse transform, Laplace inverse of s upon. I think this thing I have done someday. So you try to do this question. S square. So try to. If you have done it, then it's good. If you have not done it, then s upon s square plus a square whole. So try to do this. I'm giving you a minute. Try to do this. Okay, so how to do this question? So I've already told you that at times, if you see such questions, what you can do, one of the strategies, you know that I have told you that Laplace transform of ft upon t is simply integral from s to infinity fs dash ds dash. Okay, and you see that if I integrate this stuff up, then things would be easy for you because you have studied the Laplace transform of cos and sine. They have the term of s square plus a square, not s square plus a square whole square. So one of the good things can be that let us say that this Laplace transform is ft, this inverse Laplace transform of ft, or in other words, I'll say that Laplace transform of ft is fs, and this fs is equals to this particular thing, that is s upon s square plus a square whole square. So if I integrate this thing, I know that I'm going to get rid of this square. So I'll write 1 upon 2 here, and then I will write 2 here, and this is like s square plus a square. So deliberately, I'm integrating this thing from s to infinity. So if I integrate this up, I will simply get 1 upon s square plus a square. Okay, so this is very simple to see. This I will get 1 upon s square plus a square. Okay, and 1 upon 2 will also fall. So Laplace inverse of 1 upon 2 s square plus a square is actually equal to writing Laplace inverse of fs ds integral from s to infinity. And what it is equal to? It is equal to ft upon t. And what is ft? Ft is the Laplace transform that we want, inverse Laplace transform that we want to find. So from here I will get 1 upon 2 a, sorry, 1 upon 2a if I write a here, and if I divide by a also. So I'll get 1 upon 2 sine at is equal to ft upon t, or in other words, I'll say that my ft would be simply t upon yj sine at. Okay, I think it is easy to see. Let us try to find. Uh, let us try to find one Laplace inverse of 1 upon s plus 1 into s square plus b. So one of the ways to solve this can be to solve this. One of the ways to solve this can be to write in terms of partial fraction. That is, if I want to write it in terms of partial fraction, that I will do this a upon s plus 1 plus bs plus c upon s square plus 1. Why I'm writing bs plus c? Because this term is non-factorizable. So this is one of the way. Since this is not factorizable, so if you remember from your standard 12th class, the partial fraction for this particular term, that is s square, if you have a non-factorizable term, then it is written in this fashion. So this is one of the approach. One of the approach can be to move in this way. Another approach can be to see. I know that that's slightly tricky also. तो चलो इससे करने की कोशिश करते हैं एक बार, and then I'll try to do it in another manner also. So what it will be equals to? It will be equals to a s square plus a plus b s square plus b s plus c s plus c divided by s plus 1 into s square plus 1. And so this is equal to 1 upon s plus 1 into s square plus 1. So you get cancel. You get that cancelled. So you'll get a plus b equal to 0. This is 1. You will get you'll also get that your b plus c is equal to 0 because there is no as such s term there. And you will get a plus c is equal to 1. So your a plus c is equal to 1 and all other terms are like this. So what you can do, you can subtract this. So if you subtract this, you'll get a minus c equals to what? 0. So that implies what? A is equal to c. That implies your a is equal to c is equal to simply half. And if a is equal to c is equal to half, then your b becomes equals to minus of half. Okay, so this is how you can write it up. So what would be the Laplace inverse of 1 upon s plus 1, and here you can write s square plus 1. This will be equivalent to writing Laplace inverse of 1 upon 2 s plus 1, and then you can write minus Laplace inverse of, or you can take a plus here, you can write half outside, you can write s minus 1 divided by s square plus 1. Okay. From here, I think it's quite evident that you'll get first term you'll get 1 upon 2 e to power minus t, and the next two term you'll get 1 upon 2. This is sine t minus of cos t. I hope it is clear. Another way to this can be, yesterday I told you something about convolution theorem. So according to convolution of two functions f and g is given by integration from 0 to t fx gt minus x, I think dx. This was it. So if you use the convolution theorem also, you can do the same thing. So according to the convolution theorem, what was it? According to the convolution theorem, if you remember that the convolution of f and g is defined by fx into g of t minus x and dx. This was your convolution. And if I want to take the Laplace transform of this entire f star g, which is your convolution, then you simply get your fs into g of s. Okay, you get f. So in other words, if I want to take the Laplace inverse of fs into g of s, I will simply get my convolution of f and g. So if I use the same thing, so if I want to find the Laplace transform of 1 upon s plus 1 and 1 upon s square plus 1, it is quite easy to see that fs I can take as 1 upon s plus 1. Okay, and gs I can take as 1 upon s square plus 1. And the Laplace inverse of fs will form u ft, which is I think e to power of minus t. And if I want to find what will be the Laplace transform of this particular function, Laplace inverse of this particular function, because here you have to write f in g now. So this Laplace inverse is quite easy to see. This Laplace inverse will be simply sine. So now, if I want to find Laplace inverse of 1 upon s plus 1 into s square plus 1, it is equivalent to writing Laplace inverse of fs into gs, and which is equal to writing the convolution of f into g. And what would be convolution f into g? The convolution of f into g would be simply integral from 0 to t. What was your f? F was simply e to power minus t. What was your g? I think it was sine of t. So I'll write sine of x minus t, and I'll write dt. So what I can do, I'll do one thing. I'll use x minus t as simply some u, and this will give me d minus dt is equal to du. So you'll get integration from here to here. That is absolutely fine. And here you will get, you have to replace this t now. So your t would become simply x minus of u. This will be simply sine of u. And instead of dt, you will get minus du. So I'll write minus du. What is the lower limit? The lower limit for t is 0. So your lower limit would become x. So u varies from x, and the upper limit is t, so your upper limit is 0. So instead of taking a negative here, I'll take these limits in this fashion. Okay. Now this is being integrated from 0 to x, and e to power x is obviously it does not depend upon u, so it will get outside e to power minus u sine u. And what would be this integration? This integration is quite easy to see. I'll write it here. So 1 upon d e to power minus u sine u will be e to power minus u 1 upon d minus 1 sine u. Again, e to power minus u d plus 1 divided by d square minus 1. This is sine u. This from here you will get, if you take, so you will get a minus half, and d sine u is simply cos u plus sine u. Okay, so I think this is quite easy to see now. The derivative for sine u का derivative, गलती तो नहीं किया, चलो वैसे ही कर लेते हैं. I think that's easy to see. Is there a mistake somewhere? I don't know. E to power minus t है ना? Okay, so यहाँ मिस्टेक होगी ना. So अगर ये करेंगे तो क्या आएगा? यहाँ पे x minus t करेंगे, x minus t करेंगे तो u will come out as sorry t will t you can write as x minus of u, and here it is minus t. So instead of x minus u, you will get u minus x, right? You get u minus of x. So I'll write minus x here and I'll write u here. Okay. So if I just write u here, so what I'll get this, and here I'll get d plus 1. So it will be d minus 1. You'll get a negative, that's not an issue, but you'll get a negative here as well. So after all, you'll get an answer as e to power minus u, sorry, e to power u upon 2, and then you will get the sine of u minus cos of u. So if I write that way, so this is e to power minus x, again, not minus u plus u. So you'll get e to power u upon 2 sine u minus cos u from 0 to x. So if I write x here, so I'll get e to power minus x upon 2, e to power x upon 2, and then, sorry, I will get sine x minus sine x. And if I write 0, I mean negative, so I'll get e to power minus x is obviously there, 2 is there. What is here? Minus minus plus. So after all this, by using convolution theorem, the answer that I'm getting is simply 1 upon 2 e to power minus x plus 1 upon 2 sine x minus cosine x. Is that clear? So here also the inverse Laplace transform I'm getting in the same fashion. कुछ गलती करी क्या? ठीक है, फाइन. समझ में आई मेरी बात? यहाँ तक कोई दिक्कत किसी को? Is there any doubt? So this is the same. This is the same thing that we've got here also. Okay. So Laplace inverse, in any case, you go by any sort of formulation, you'll get the same answers. Don't worry about it. Okay. Now I'm going to teach you a little bit difficult thing. Probably may not derive it, but uh, it is sometimes referred to as Bromwich integral. Okay. So that is also one of the ways to do that. Do this kind of integration. This is called as Bromwich integral. So I'll do that also for you. Let me just write it up first. Okay. So what is Bromwich integral? So I'll write it only without proof. Okay? Okay. So Bromwich integral, write down without proof. If time allows, or sometimes if you are again doing complex analysis, I'll do it there itself. Okay. So what is Bromwich integral? So here it is. So for example, so your inverse Laplace transform can also be found using contour integration, can also be found. And this is the last resort, I would tell you. This is the last resort that I would tell you. It's not essential that you go by this method, but it is the last resort that you can think of. Okay. So this is what I'm doing. So for example, inverse Laplace transform can be found using this contour integration. Okay. And in this, the inverse Laplace transform is given by a contour integration that I'm going to write it just now, which is called as Bromwich integral. Okay. So this is it. So I'll write it here. The inverse Laplace transform is, sorry, can be expressed as the contour integral can be expressed as the contour integral integration c minus iota infinity to c plus iota infinity 1 upon 2 pi iota outside, and then you have this fs e की power ts ds. Just remember this result, don't worry about it, I will let you know, where fs is the Laplace transform of ft. So if you want to find your inverse Laplace transform of a function, then it becomes equal to this kind of contour integral. And this is actually done over a Bromwich contour, and which is from C minus like this. So this is a kind of contour that we actually use in order to, this is sometimes referred to as Bromwich contour. Bromwich contour. And by using the contour integration technique, we actually solve this particular integration. So here it is C minus iota. So take sorry. You take some C plus iota t, and then you take t tends to infinity, and if you solve this particular under this particular contour, in order to find my inverse Laplace transform of fs, I have to solve this contour integration. And if you remember, what is your contour integration? Contour integration is equal to 2 pi iota into sum of residues. If you remember that the contour integration is equal to 2 pi iota into sum of residues for all those isolated singularities which lie inside these contours. Okay, so an equivalent to this particular statement can be that if I want to find the inverse Laplace transform of a function, the inverse Laplace transform L inverse Fs is equal to Ft is what? Is given by what? So basically what one needs to find is the sum of residue of the function. So this is the function is given by the sum of residues of e की power ts fs at the poles of fs. Is that clear? So you remember this kind of statement. So all you need to find whenever you are supposed to find an inverse Laplace transform, just try to find the sum of residues of e की power ts into fs at the poles of fs. Is that clear? Because you know that e की power ts is an analytic function, entire function. So it is not going to encounter any sort of singularity. Fs may attain some singularities. Those isolated singularity find the residue of this entire function. So if you find the residue of this entire function, then 2 pi iota into sum of residues, this will give you the value of this integration. 1 upon 2 pi iota and 2 pi iota get cancelled. So only thing that is left is the residues. So if you just find the residue of, if you just find this integration, or in other words, you just find the residue. You just find the residue of function fs into e की power ts. And then if you find this up, then you'll be able to find the inverse Laplace. I'm not doing the derivation because I'll then move over it. Then it will be a slightly different topic altogether. Probably if time allows, I'll do it in complex analysis. But right now, just accept the fact. Just accept it as a fact. Is that clear? Okay, good enough. अब देखो एक काम करते हैं, लेट अस ट्राई टू, कहाँ गए क्वेश्चन, कौन सा चल रहा था जो हमने दो तरीके से किया, दो तरीके से किया. देखो एक क्वेश्चन था जिसको हम लोगों ने क्या किया, बाय सिंपली वी हैव डन इट यूजिंग partial fractions. Then we did it using convolution theorem. Then let us do it using the Bromwich integral. However, the Bromwich integral is the last resort. Don't try to do it every time because probably you may not be well acquainted with it, and then the question may get wrong in exam. So it's better to not use it if you are not quite aware of it, and if you have not done enough practice over it. So, but right now, since I've taught it, so this is your, if you want to find the Laplace inverse of this particular function, first thing that you need to find is what are the poles of Fs. What are the poles of Fs? So what are poles of Fs? 1 upon s plus 1 and s square plus 1. What are the poles of it? So its poles are equal to -1 and plus minus iota. Clearly, you can see that here your function will be singular. And in order to find the Laplace transform of this particular function, all you need to find is that sum of residues uh, about the poles, that is at s equal to -1, s equal to plus minus iota for what? For the function e की power ts divided by s plus 1 into s square plus 1, right? ये बताया था मैंने. So you have to find the sum of residues of the function e की power ts into fs at the poles of fs. So what is your poles of fs? Poles of fs are simply you have to find like s. Where does it attain singularity? So there are isolated singularities at s equal to -1 and s equal to plus minus iota. Okay, and so this is what I'm going to do now. I'm going to find the residue. So residue first at f s equal to -1. So residue of function at s equals to -1, what it will be? It will be s tends to -1, s plus 1 into e की power ts divided by s plus 1 into s square plus 1. And what it will be? It will simply be equals to e की power minus t upon 2. What would be residue of function at s equals to iota? So it will be simply limit, because these are sub simple poles, s minus iota, s tends to iota, sorry. This is s minus iota into e की power ts divided by s plus 1 and s square plus 1, you can write s minus iota into s plus iota. So this would get cancelled, and eventually you're left with e की power iota s iota t divided by 1 plus iota, and then you have this 2 iota. And another thing, that is residue at a function at s equal to minus iota, would be simply limit s tends to minus iota. Remember, these are all the simple poles, so therefore I'm using the formula for the residue for the simple poles. So residue for simple poles is given by, if z is equal to z naught is a simple pole for function fz, then the residue is given by limit z tends to z naught, z minus z naught into f of z. This is how you get the this is the formula for the residue for the simple pole. And how do you get it for multiple poles? So let us say that my z naught is a pole of order m, then the residue is equal to m minus 1 factorial dm minus 1 upon dz m minus 1 z minus z naught raised to power m fz, and this all thing has to be evaluated at z equal to 0. So this is how you get the residue of the function fz at z equal to z naught, where z naught is a pole of order m. So for pole of order 1, you simply have to find this limit z tends to z naught, z minus z naught into fz. So here you will get e की power ts divided by s plus 1, s minus iota, and s plus iota. So s plus iota would get cancelled. This is s minus iota. So if you use s minus iota, I'll get e की power minus iota t divided by 1 minus iota, and this is minus. You have to sum it all. So I'm summing it up. So e की power iota t minus e की power minus t by 2 plus e की power iota t, and then I'll take this thing e की power iota t upon 1 plus iota into iota, and then I have this plus e की power minus, in fact I'll write e की power minus iota t upon 2 iota 1 minus iota. And finally, this is equal to writing e की power minus t by 2 plus if I use this thing, so I'll take 2 common out, and This is e की power iota t divided by iota minus 1, and this would be minus e की power minus iota t divided by 2 has been taken common, so don't worry about it. This would be iota plus 1. So this will account for e की power minus t by 2 plus 1 upon 2. And then you take LCM for this. This will become minus 2. And here you will get iota e की power iota t. So I'll write iota e की power iota t minus iota e की power minus iota t. This is one thing. And then you have this, if you take plus e की power iota t and plus e की power minus iota. Okay, so this is what it is. Now, if I just solve it somehow, I will get e की power minus iota t, e की power minus t upon 2 plus 1 upon 2. Remember, this is equals to what? So this is equals to minus, this is equals to minus. So if you remember, e की power iota t minus e की power minus iota t is simply 2 iota sin t. So this is 2 iota sin t. Iota is already there, so minus, 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 plus. So you simply get a sin t here. And here, if you know this is cos t, so you get a minus cos t. So this is what you got from other ways also, like convolution theorem also, you got the very same result. Okay. From the basic approach, that is by just trying to divide this particular term, or just trying to take distribute it in terms of fractions whose Laplace transform you know. So all these things are quite easy to see. Okay, so this is the beauty of this particular method. However, this particular thing needs to be explained. This particular integral probably I have not discussed in the complex analysis class, but I may discuss it any day when we are going to revise the complex analysis. Okay, now now we are heading towards the end of it. So let us do a few questions and then we'll summarize this entire chapter. And then we'll see the previous year question in the separate session. So let us try to do some questions on inverse Laplace transform. Okay, so let us try to do some more questions on inverse Laplace transform. Try to find the inverse Laplace transform of, let us say, 2s plus 1 divided by s square plus s plus 1 का whole square. So if you remember, if it's just see it, so s square's derivative is 2s and s derivative is 1. So what you can do, you can try to integrate this. So I've told you the Laplace transform of ft upon t is simply integration from s to infinity fs dash ds dash. Okay, and if you do that, so if I integrate this thing, I will get what? I will simply get from s to infinity, I will get, this is my derivative and this is my function. So it will be equals to minus of 1 upon s square plus s plus 1. From where to where? From s to infinity. So again, if I do it, I'll get 1 upon simply s square plus s plus 1. So what would be Laplace inverse of this integration, which is 1 upon s square plus s plus 1? It would be simply ft upon t. And what is ft? Ft is the Laplace Laplace transform of, let's say, ft is fs. Then what is ft? Ft is the Laplace inverse of fs1. So this is what we want to find. This is what we want to find. This is ft is what we want to find. So what would be the Laplace inverse of this particular thing? So if I just try to make it in a perfect square, so this will be s plus half the whole square. Then I will write root 3 by 2 the whole square here. This is simply ft upon t. So if I write this in this fashion, I will get what? I will get that ft upon t is simply, if I use root 3 by 2 here, and if I divide by 2 upon root 3 here, so it will be 2 upon root 3 sine of root 3 by कहाँ गया ये? अच्छा, root 3 by 2, and there is also s plus half also is there. So s has been replaced by s plus half. So if you remember that if I want to simply write, uh, 2 minutes ago, if I want to simply, if you remember this thing, देखो, अगर हमारा इसकी जगह अगर सिंपली 1/s² प्लस √3/2 का होल स्क्वायर होता, then probably, and then you have to write √3/2 here also and 2/√3 also. So you would have simply written it as sine of √3/2, and you would have written 2/√3. But if you see that there is also some s plus half given here, so s plus half is also given here. So you have to use your shifting theorem also here, because you see that here instead of s, you are given s plus half. That implies that there has been a shift. There has been a shift. So if you remember that, if I correctly remember that Laplace transform of e to power at ft is what? It is equals to what? It is equal to f of s minus of. If you remember, this was, I think, your first shifting theorem. So from there, if you see, instead of s, you have s plus half. So what does it imply? It implies it is 2/√3 e to power minus half of t. And then I think this is sine of √3/2t is equal to ft upon t. So your ft would be simply what? Ft would be simply ft, which is the Laplace inverse of your fs, which is required, is 2t upon √3 e to power minus t upon 2 and sine of √3 upon 2t. Is that clear? Is that clear or not clear? So if you remember, if it was multiplied, if ft was multiplied by e to power at, then your Laplace transform is not fs, it is rather f of s minus of it. So your f of s is here f of s plus half. It implies instead of ft, you also had a term of e to power minus half t. So that sums up your lecture first, and then we'll do a few more questions, and then in the lectures too, in the next few lectures, next few last lecture. Okay, so I'll finish it off in this particular lecture. So I'll because there is a lack of time, so I'll join you in the next session.